Welcome to part 2 of the Avalanche Level 2 weather module. In the following, we will focus on mountain weather. When we say mountain weather, we mean the interaction between large-scale weather patterns in the mountains and how mountains create their own weather. So let's get started. As was previously mentioned, water is found in trace amounts in the atmosphere. Importantly, water is found in all three phases, solid, liquid, and gas, simultaneously in the atmosphere. Water is one of the few materials that can naturally be found in all three phases simultaneously. Water typically exists very near its triple point, the combination of temperature and pressure, where water exists in all three phases simultaneously. This is very unique and gives water many of its unique characteristics. The diagram on the right is the phase diagram for water. As you can see, at 32 degrees Fahrenheit, water exists in all three phases. Slight changes in pressure or temperature around the triple point drive phase changes in water. The main physical processes we are concerned with are melting and freezing, the change from solid phase to liquid phase, vaporization, the change from a liquid phase to a gas phase, and sublimation, the change from a solid to a gas. A couple of key concepts that we need to discuss are moisture capacity and relative humidity. Moisture capacity is the amount of water vapor that air can hold at a given temperature. As air temperature increases, moisture capacity increases. As air temperature decreases, moisture capacity of air decreases. Relative humidity is the amount of water vapor in the air relative to its moisture capacity. So 50% relative humidity, as an example, means that the air has half the water vapor that it could potentially hold at that temperature. Saturation is 100% relative humidity. This is also known as the dew point. Since the moisture capacity is a function of temperature, this means that relative humidity and dew point are also a function of temperature. So for example, as clouds in the atmosphere collide with mountains and are forced upward, the temperature decreases. This will reduce moisture capacity of the clouds. Excess water vapor will be forced out of the vapor phase and into the liquid phase and will fall as rain or snow. Let's look at some specific examples. As you can see, air at 10 degrees centigrade has a moisture capacity of 9.4 grams of water vapor, roughly twice the moisture capacity of air at 0 degrees centigrade. So if saturated air at 10 degrees centigrade is cooled to 0 degrees centigrade, the moisture capacity is reduced by 50%. The excess water vapor is given off as rain or snow. If the air is reheated to 10 degrees centigrade, the remaining water vapor is 4.9 grams compared to the moisture capacity of 9.4 grams. The relative humidity is now 52%. So air that was saturated is now considerably drier due to the cooling and reheating effect. This is exactly what happens when air rises on one side of a mountain and descends on the other side. This heating and cooling effect as air rises up one side of the mountain and down the other is called adiabatic cooling. The adiabatic lapse rate is the rate at which air changes temperature with altitude. As you can see from the slide, the rate is different for saturated air versus unsaturated air. So when warm, moist air starts to ascend up the side of a mountain, it cools at roughly 6 degrees centigrade per kilometer of altitude gain. As it cools, the moisture capacity is reduced and excess water vapor is lost in precipitation as either rain or snow. As the cool, dry air moves down the mountain on the leeward side, it heats up at roughly 10 degrees centigrade per kilometer of altitude lost. The effect of this is that air on one side of the mountain is drier than air on the other side, and one side of the mountain will get much more snow and rain than the other side. So to summarize, air is lifted as it collides with a mountain. As it is lifted, it is cooled, its moisture capacity is reduced, and excess water vapor is given off as precipitation as either rain or snow. This is a key concept in mountain weather that we will come across many times during this class. So as we mentioned, as temperature decreases, the moisture capacity of the air decreases, and water is released as rain or snow. When water vapor is released at the appropriate temperature, snow crystals can form. These snow crystals can take several forms as shown on this slide. The exact form depends on the temperature, humidity, and other material in the air. Note it is possible that more than one form can be present at a time. The first form, condensation of freezing nuclei, is the most common for snow formation. Water vapor condenses on small particles of dirt, dust, or other material in the air. These small particles act as a seed for snow crystal formation. The second form is vapor deposition. Once ice crystals form, they will attract water droplets. These water droplets then freeze on the ice crystal, and the ice crystal grows. This is how we get graupel or hail. The third form, supercooled water, only occurs at very cold temperatures higher in the atmosphere. In this case, the supercooled water freezes on contact with a larger ice body. This is how we get riming. Let's look at each of these mechanisms in more detail. Snow crystals begin to form in the clouds. Clouds are formed by water droplets when the air is supersaturated. The water droplets are formed by condensation of water vapor on condensation nuclei. The nuclei, either a particle of dirt or some other material, attracts water vapor. The water vapor bonds to the condensation nuclei and a water droplet is formed. As more water vapor molecules bond to the water droplet grows in size until the weight of the droplet gets to a point that gravity results in it falling to Earth. When the temperature in the atmosphere is below 0 degrees centigrade, the water vapor condensing on the condensation nuclei forms tiny ice crystals. Note in this case the nuclei are called freezing nuclei and have more unique characteristics to promote ice crystal formation than the condensation nuclei discussed in the previous slide. As an ice crystal forms, its growth is determined by two mechanisms: direct transfer of supercooled water droplets due to vapor pressure differences, and collisions between ice crystals as they grow in the atmosphere. Direct transfer is the primary growth mechanism. Since the vapor pressure is higher at the surface of the water droplets than at the surface of the ice crystals, water molecules transfer from the water droplets to the growing ice crystal. As the crystals grow, vapor pressure is non-uniform across the surface of the crystal. There are lower vapor pressure at places of high convexity, such as sharp-pointed areas. These areas grow faster than other areas, resulting in the snowflake shape shown on the lower left that we are familiar with. As the ice crystals grow, they eventually get to a size where they fall under the influence of gravity. As they fall, they gain mass by colliding with supercooled droplets. The supercooled droplets freeze to the ice crystal in the process called riming. The ultimate shape that the snow crystal obtains in the atmosphere depends on complicated physical processes, but the most important variable is temperature. Growth occurs in two basic directions: in the basal plane of the ice crystal or perpendicular to it, as shown in the diagram. Plate-like crystals grow along the axes of the basal plane, while rod or needle-like crystals grow along the axes perpendicular to the basal plane. Crystals are cataloged based on some common forms. Examples are shown on this slide. As you can see, plates, dendrites, and stellar forms all have growth in the basal plane, while columns and needle forms have preferential growth in the A and C plane perpendicular to the basal plane. It is the difference in growth rates along the different axes that determines the ultimate shape of the ice crystal. These growth rates depend on temperature and vapor pressure. A more complete list of crystal forms can be found in the appendix of the SWAG manual. So why do we care about these crystal forms? Well, different crystal forms have differing degrees of stability in the snowpack. Dendrites and stellar forms, for example, typically degrade into rounded grains that bond well in the snowpack and increase stability. We will discuss this in more detail in the snow science modules. One common form of snow crystal we see on Mount Hood is riming. As mentioned previously, riming occurs when supercooled water collides with an ice crystal in the atmosphere and freezes to the ice crystal. As these ice crystals cycle through the atmosphere, they go through differing thermal layers. Some of these thermal layers will drive growth preferentially along the basal plane, others along the axis perpendicular to the basal plane. A capped column, as shown in the bottom left, occurs when the ice crystal goes through a cold layer that drives growth along the perpendicular axis, then goes through a warm layer. The warm layer drives growth along the axis of the basal plane, creating a cap on the column. If the capped column then collides with supercooled water droplets, rimed ice particles will form on the cap as shown. On Mount Hood, you will see riming commonly on signs and other structures, where the rimed ice crystals grow into the wind as the water vapor impinges on the growing ice crystals mentioned previously. Another form of riming is grauple, shown here. These are nature's ball bearings. A layer of grauple, when covered by subsequent layers of snow, can act as a weak layer that could fail and lead to an avalanche. Grauple is formed by repeated riming of the ice crystals until all branches have been filled in a spherical shape results. In the previous module, we talked about the concept of radiation balance. Recall that this was the net sum of radiation absorbed by the Earth's surface. Solar radiation that reaches the Earth's surface is absorbed and heats up the surface. Long wave or blackbody radiation is emitted by the Earth's surface and cools off the surface. This effect is non-uniform. Factors such as angle of incidence and the albedo or reflectivity of the surface vary and can influence the radiation balance. The radiation balance also fluctuates during the day as the Earth rotates. During daylight hours, there is usually a net positive balance due to solar radiation. During nighttime hours, there is usually a net negative balance since solar radiation is reduced and long-wave radiation dominates. Note this nighttime long-wave radiation can reduce the surface of the snow to a temperature lower than the air temperature. Because of this diurnal fluctuation, the temperature at the snow surface fluctuates. This slide shows the fluctuation of the snow surface temperature because of diurnal temperature variation. The key point here is that for temperatures near or below 0 degrees centigrade, there is a temperature gradient that is created near the snow surface. This temperature gradient is the biggest factor in determining the nature of the snow crystal structure. A temperature gradient less than 1 degree centigrade per 10 centimeters will result in rounded crystals. These form strong bonds and result in a stable snowpack. A temperature gradient greater than 1 degree centigrade per 10 centimeters results in faceted crystals. These do not form strong bonds and can result in weak layers that can fail and lead to an avalanche. Also note that if the daytime temperature is greater than 0 degrees centigrade, the surface of the snow will melt. As the surface refreezes at night due to the diurnal temperature fluctuation, a melt-freeze crust will form. Much more of this in the snow science modules. If the temperature gradient created by the diurnal temperature variation is greater than 1 degree per 10 centimeters, a phenomenon called near-surface facetting can occur. If these near-surface facets are buried by a subsequent snowfall, they can form a weak buried layer that can persist for weeks or months. This is the classic recipe for a large slab avalanche. Wind and wind transport plays a very important role in avalanche formation. As we discussed previously, wind flows from areas of high pressure to areas of low pressure. When the wind hits a mountain range, the mountains steer the wind. Ridges can increase wind velocity and valleys can cause channeling. All of this impacts the deposition of snow in the mountains. On Mount Hood, the prevailing winds are usually from the west. This means that eastern-facing slopes will typically have much deeper snow as the wind lifts the snow from the west-facing slopes and redeposits the snow on the east-facing slopes. This is very critical to remember. Wind can deposit snow 10 times faster than precipitation. This will load a slope very quickly, rapidly increasing the stress on any weak layers. Snow transport starts when the wind reaches about 10 miles an hour, and optimal transport is between 25 to 45 miles an hour. There are several terms used in snow science to describe this wind transport. Rolling occurs in light winds and is the creep-like motion of dry snow particles. Typically, the transport layer is 1 millimeter thick or less. Saltation occurs when the winds reach 10 to 5 meters per second range, somewhere between 25 and 45 miles an hour, and particles bounce along the surface. In this case, the transport layer is 1 to 10 centimeters thick. Snow in the layer is subject to a large amount of friction, so the crystal structure is destroyed. The snow particles bond together and form strong cohesive slabs when the snow is redeposited. For higher winds, greater than 45 miles an hour, the snow forms a turbulent suspension that can be meters thick. In this case, the snow can be transported large distances. So that brings us to the end of weather part 2. We will now move on to discuss how we use this weather information to assess avalanche risk.